Hey guys, today we're talking about our parent functions and our transformations. So we're going to talk about a couple parent functions, and then we're going to look at what all of our transformations are and what those look like for those specific parent functions. So the first parent function that we have is the linear function. So I've got it graphed for you already. The equation is y equals x. If you're looking at it, the domain for it would be from negative infinity to positive infinity. And the range would be the same thing from negative infinity to positive infinity. To help me memorize my parent functions back when I was in high school, I would put the equation, the graph in the word. So I think about the L in linear functions and I write it like this, with the L being a line. Another thing is that linear functions are also sometimes referred to as the identity function. So that's another name that you may see for it, the identity function. The next one we have is the absolute value function. It's graphed over here. It makes that V shape. Y equals the absolute value of x. The domain is also negative infinity to positive infinity. Our range is a little bit different though. For our range, we're going to go from 0 with a bracket because that point is included in our range. And then we're still going to go up to infinity. Those arrows do show that we're going up in that same pattern up to infinity, but we start at 0. We don't go below 0 for our range. For absolute value, I think about the V in absolute value. So it looks like this when I put it in the word absolute value. Next is the quadratic function. So for the quadratic function, we have y equals x squared. The domain is also negative infinity to positive infinity, and the range is also from 0 to infinity. For the quadratic, I think about u in quadratic because our graph makes that u, that parabola shape. So quadratic. After quadratic, we have the square root function. So y equals the square root of x. This one is a little bit different. We have a very specific point where our graph starts at 0, 0. So my domain is going to go from 0 to infinity. I've got a bracket there because 0 is included in my domain. We do include that point. And my range is also going to go from 0 to infinity with a bracket on the 0 because it's included in the range. When I write this one, I think about the r in root, and it comes up and over like my graph comes up and over. So far we have linear, absolute value, quadratic, and square root. After that, we have the cubic function, y equals x cubed. For our cubic function, our domain is from negative infinity to infinity. Our range is the same, negative infinity to infinity. We've got arrows on both ends, showing that it goes both ways. And this one is kind of a bit of a stretch for how I put it in the word, but I think about the U. It goes up on the right side, and then the left side kind of goes down, like the U had been dropped down on that side. So I kind of write it like that for the cubic function. Next is the cube root function. So we have y is equal to the cubed root of x. Our domain is also negative infinity to infinity, and same for the range. The arrows on the either end show that we're going to go off to negative infinity and positive infinity for all of those. And for cube root, I think about the r like I did in the square root, but I put a tail on it since the cube root has the negative values with it too. And our last one that we're going to look at is our rational function. So it's y equals 1 over x. Our rational function has asymptotes. One goes up and down on our axis, The other one goes across on our axis, and they kind of make the T shape that we have in our word. So I think about the T in rational for how I draw my graph. The domain and range for this one is a little bit different. Because we have those asymptotes, we do have to kind of adjust how we write our domain and range, and we're going to have some unions. So I'm going to go from negative infinity to 0, union, 0 to infinity, and the same thing for the range, and it's because that's where my asymptote is for my domain and for my range. Now, all of these are parent functions, but every parent function can be transformed based off of different things that happen in your equation. So that's what I have listed here is kind of a skeleton version of an equation, and it's got all of the different transformations that can happen. So the first thing is that if you have a negative in the very, very front of your equation, that is going to reflect over the x-axis. So that makes our graph go from wherever it is and reflect over the x-axis, so that kind of takes it and turns it upside down. You could also have an a value that you multiply by out in the very, very front. If that happens, if it's between 0 and 1, that's what we call a vertical compression. Another word you may see is shrink instead of compression. And if it's greater than 1, that is a vertical stretch. If I have a negative that's like inside the function, so like inside the squared, inside the root, inside the absolute value, then that negative is going to, instead of reflect over the x-axis, reflect over the y-axis. Same thing, I could have a value that I'm multiplying by that's in the root, in the cubed or squared, inside the absolute value, inside the bottom of the fraction with the x. And instead of it being a vertical compression or stretch, that one's going to be a horizontal. And this one is kind of the opposite of the vertical shrink or stretch. So if it's between 0 and 1, so 0 less than b less than 1, that one is going to be a horizontal stretch. And if it is greater than 1, b greater than 1, that's where we're going to have our horizontal compression or horizontal shrink. I'm going to write shrink because it fits in the box a little bit better. The other thing is the way we talk about these is a little bit different. So if I have a vertical stretch or vertical compression, so let's say my A value was like 6, I would say I have a vertical stretch by 6. Or my A value was 1/2. I have a vertical shrink by 1/2. When I get to my horizontal stretches and my horizontal shrinks, I talk about it a little bit differently. So I would say that I have a horizontal stretch or shrink by 1 over whatever my b value is. So if b was, let's say, 7, then that would be a horizontal shrink, and I would say that it's a horizontal shrink by 1/7. So even though b is 7, I talk about it as a shrink by 1/7. Or if, let's say, b is 1/2, that would be a horizontal stretch, but I say it's a horizontal stretch, I would do 1 over 1/2, which would in turn be 2. So it's like the flipped version of whatever you have. So it's just a little bit different than how we talk about the vertical stretches and shrinks. Okay, then if I have an h that I'm adding or subtracting in the root, in the squared or cubed, in the absolute value, in the fraction, then that is going to move it to the left or to the right. If I have minus h, it's going to move it to the right. If I have plus h, it's going to move it to the left. And if I have a k on the end, behind the squared, behind the cubed, behind the root, behind the absolute value, that's going to move it up or down. So if I have minus k, that's going to move it down. If I have plus k, that's going to move it up. So what we're going to do is we're going to look at some examples where we're going to state the parent function, list the transformations, and then we're going to graph it. So for this first one, we've got x squared plus 3. My parent function there is the quadratic function. So that is y equals x squared. And anything outside of that x squared is a transformation. So that means that this plus 3 right here is going to move my graph up 3. So when I come over here and graph my quadratic parent function, I have the point 0, 0, 1, 1, 2, 4, 3, 9. I can mirror those points, negative 1, 1, negative 2, 4, negative 3, 9, and this is my parent function, my quadratic, my parabola. And if I'm going up 3 units, I'm just going to take all of these points and move them up 3 units from where they were. And that's my new function. So moving up or down, left or right, it's pretty easy to apply those transformations. Example 2, I have 3 times the absolute value of x plus 2. So my parent function is the absolute value function. Y equals the absolute value of x. This plus 2 that's inside the absolute value is going to shift my graph to the left 2. And this 3 that's out in front of it is a vertical stretch by 3. There we go. So when I graph all of this, my absolute value makes that V shape. So I start at the origin and just have my V shape. It goes like through the point 1, 1, 2, 2, 3, 3. And on the negative side, it goes through the point negative 1, 1, negative 2, 2, negative 3, 3. So when I move this one, when I move it to the left 2, that, like I said, is the easy transformation, but the vertical stretch is the one that's a little bit more difficult. So I'm going to take my graph and what would normally go like up 1 or up 2, I'm going to stretch all of those distances by a factor of 3. So instead of going up 1, now I'm going to go up 3 units. So when I shift over to the left 2, that point now is going to be up 3 units. And what was up 2 is now going to go up. I'm going to stretch that by 3, so it's going to be up 6 units. And what was normally up 3 units is now going to be up 9 units. So I'm taking it and kind of stretching it out by whatever my factor was that I multiplied by. So since I had a stretch by 3, I'm taking all of those and kind of stretching them 3 times how far up they were from the axis originally. Okay, example 3, my parent function is the cubic parent function. So that's y equals x cubed. This minus 1 is going to shift it down 1, and this plus 1 is going to shift it to the left 1. So my normal cubic function has a point 0, 0, then 1 cubed is 1, 2 cubed is 8, negative 1 cubed is negative 1, and negative 2 cubed is negative 8. So it makes our cubic function. And then I'm just going to take all those points and move them left 1 and down 1 to get my new graph. Some of the points do overlap a little bit. That's totally fine. There's my new graph. Example 4, we have the square root function. So that starts as y equals the square root of x. I've got a plus 3 that's going to move my graph up 3. And I've got a minus 2 that's going to move it to the right 2. So when I draw my parent function, I'm going to be a little bit more particular about the points that I pick. So I know the square root of 0 is 0, the square root of 1 is 1, but like I don't know exactly what the square root of 2 is. So instead of picking 2, I'm going to pick a number that I do know the square root of, which is 4. So my next point is going to be 4, and the square root of 4 is 2. And then I know the square root of 9 is 3. So I'm going to be a little more selective in the points that I pick. I'm going to pick points that I know will give me nice, pretty points instead of trying to deal with decimals. Work smarter, not harder. Don't work with decimals if you don't have to, you know? So there's my graph, and then I'm just going to move it to the right 2 and up 3. So I get this graph right here. Okay, got 2 more. Example 5, we've got the quadratic function again. And when I'm looking at this one, I still have 2 transformations that are happening here. This negative is its own transformation. It's going to reflect over the x-axis. And the 2 is a vertical stretch by 2. What I see happen a lot is people forget that that negative is its own transformation and just take the negative 2 and make it one transformation altogether. So remember, the negative is its own thing, the 2 is its own thing, and they're separate transformations. So I've got my quadratic parent function. We've already graphed it once, so I'm just going to put the points on real quick. 0, 0, 1, 1. You've got 2, 2, 4, 3, 9. -1, 1, -2, 4, -3, 9, and you can connect them to get your parabola, your quadratic. And when I am graphing this one, it's going to reflect over the x-axis. So instead of opening up, it's going to open down, and we've got that vertical stretch by 2. So the points are now going to go down, and they're going to go twice as far from the axis as they normally did. So this one normally went up 1, so now it's going to go down 2. And this one normally went up 4, so now it's going to go down 8. And that's how I get my new graph. Then my last one is a little bit different. We're not going to graph this time. This time it says write the function whose graph is the graph of y equals x squared, but is shifted to the left 5 units, shifted down 6 units, and reflected over the axis. So I'm going to start with like my base equation, y equals x squared, but I'm going to give myself some space that I can fill in those transformations. So the first one says it's shifted to the left 5 units. So if it's shifted to the left 5 units, I'm going to put a plus 5 in the parentheses with the x. Then it says that it's shifted down 6 units. So when it's shifted down 6 units, that's going to be a minus 6 outside the parentheses after the squared. And it says that it's reflected over the x-axis. So we just talked about that. Reflecting over the x-axis is where we have the negative in the front. So I'm just going to put a negative in front of my parentheses, and that would be my equation. So I start with my basic equation and then fill in my different transformations as I kind of read them through the sentence. So that's it for this set of notes. Make sure you get started on your assignment that goes with this, and you guys have a good day.